Welcome to our third video on carbonyl compounds. In the previous video, we saw some of the reactions of carbonyl compounds. In this one, we'll see the remaining common reactions. Now, beyond the reactions I have discussed and the ones I'm going to discuss now, there are several other reactions of carbonyls that we may, never talk about. For some of us, until we do chemistry at a higher level, we'll never see them. There are many condensation reactions they undergo that we would not talk about. There are several other oxidation and reduction reactions. The reactions are very many. But for relevance sake, I'm going to stick to my outline. So now I'll tell you about reduction of carbonyl compounds. What do we get when carbonyl compounds are reduced? Well, there are various possible outcomes when you carry out this reaction. And if you remember, we said before that when primary alcohols are oxidized, they become alkanals and then finally alkanoic acids, whereas when alkanones are oxidized, when secondary alcohols are oxidized, they become alkanones. Now, based on this, if we were to take this alkanal back or take the alkanone back, that would be reduction. So it follows that reduction of alkanals and alkanones will give alcohols, but of course different classes of alcohols. So that if I were to start with, let's say this, which is propanal, as well as this. So I have drawn a 3-carbon alkanal and a 3-carbon alkanone. If these two were subject to treatment with a reducing agent, then they would both become reduced by simple addition of hydrogen. If you remember basics in chemistry, it is said that the addition of hydrogen to a substance is reduction. So the reduction that's going to take place here will be in the form of addition of hydrogen. So that in this first case, I'll get CH3, then beyond that, CH2, and then on this last carbon, I have CH already. Up there, there's double bond O, so I have single bond OH, and then down here, H. So if you check what has happened there, the only major conversion that's taken place is 2 hydrogens have been added. That product you are looking at is called propan-1-ol or 1-propanol, and 1-propanol is a primary alcohol. The alcohol, one video can tell you why this is a primary alcohol. Then in this case, I'll have CH3, then C. My double bond O becomes single bond OH, and then down here I have H, and then on that side I have CH3. This time around the compound is called propan-2-ol. So propan-1-ol is primary but 2-ol is secondary, and they are the products we get from the reduction of these two guys. So it follows that if we were to reduce an alkanal or alkanone, all we would need to do is introduce 2 hydrogens to the carbon bearing the oxygen. Now, this is just one way of reducing them, adding hydrogens to them using common reducing agents. Another option we have that is of importance is reduction of a carbonyl compound, not into alcohol, but into alkane. So the question is, can carbonyls be reduced into alkane? The answer is yes. And what would we need? What reagents can we use to convert a carbonyl into an alkane? If you were to convert a carbonyl into an alkane, 2 common reagents you could employ are zinc, amalgam, or you say amalgamated zinc, in the presence of acid. So this is amalgamated zinc and acid, or you say zinc, amalgam, and acid. Then your second option will be to use N2H4, which we saw in the first carbonyl video as hydrazine. You could use it along with base. So to convert carbonyls directly into alkane, I said we could use amalgamated zinc and acid, or we use hydrazine and base. When we use amalgamated zinc and acid, we call the reaction Clemenson's reduction. That's the Clemenson's reduction. But when we use hydrazine in base, we call the reaction the Wolff-Kishner reaction. Wolff-Kishner reaction. So there's the Wolff-Kishner reduction and there's the Clemenson's reduction. The reagents we use for the two are different, but the outcome is the same. And what's the outcome? Conversion of our carbonyl into an alkane. So look at this now. Interestingly, we already have two carbonyls on the board. Let's say I'll adjust one of them a bit. Let's say I adjust this one to become butanone. So this is propanol and that's butanone. If propanol is subjected to treatment with amalgamated zinc and HCl, or even with the other reagent, any of them you put there, you are very sure that an alkane will come out from this reaction. And if you listen to the name of the alkanol, propanol, then you would know the name of the alkane that will be formed, propane. So there's correspondence, there's no loss of carbon atoms, so that all that needs to occur here is oxygen off and two hydrogen atoms on, so that we have CH3, CH2, CH3. That's the corresponding alkane, and its name is propane. In this case, where we have butanone, let's say this time I'm using N2H4 OH-, so that's hydrazine in base, and hydrazine in base, of course, that will be the Wolff-Kishner reduction, so that on that side, as product, I am going to get the corresponding alkane. Now, the corresponding alkane will be drawn like this, that's C4 and H10. Its name is butane. So in both cases, notice that I have removed oxygen from the carbon bearing it and simply replaced it with two hydrogens. That gives me the corresponding alkane. However, it is important to remember that I am not saying by this that hydrazine in base can only be used for alkanones and then amalgamated zinc for, no, any of them, any of the reagents for any of the groups of compounds will give you alkanes. So carbonyls generally can react with these two guys to give alkanes. So that's the end of reduction. If you need to pause the video for a minute, you could do so. Otherwise, I'll continue to the next set of reactions. In this next set of reactions, we will see our carbonyl compound reacting with base, just base, nothing else. So when a carbonyl reacts with base, something very interesting happens. And of course, the outcome will depend on the nature of the carbonyl compound. See what I mean by that? If I were to draw a carbonyl, or let's say I draw these two compounds, look at these. CH3, CH2, COOH, and then let's say CH3, CH2OH, and then CH3, CH2, NH2, CH3, CH2, CHO, and then CH3, CO, CH3. Consider these compounds. I want to use them to show us something that would help us understand the next set of reactions. Now, in this first case, we have an alkanoic acid. In this alkanoic acid, of course, we know this is carbon 1, here's carbon 2, and that's carbon 3. But that's by IUPAC nomenclature. By trivial nomenclature, we usually leave out the functional group And after the functional group, the first carbon we meet, we call it the alpha carbon. The next one is called beta, and so on. Now, as this carbon is called alpha carbons, or alpha carbon rather, the hydrogens attached to it are called alpha hydrogens. So we say this compound has 2 alpha hydrogens. What about this compound? Again, we'll leave out the functional group, OH. Then carbon 1 in this case happens to be the alpha carbon. So carbon 1, carbon 2, alpha carbon could be anything. But the most important thing is that you remember that alpha carbon means the first carbon after the functional group. So in this case, it happens that carbon 2 is the alpha carbon, whereas here carbon 1 is the alpha carbon. What about the case of this guy? Functional group of alpha carbon. The alkanal, functional group of, then this is the alpha carbon. So does this alkanal have alpha carbons? Yes. And on that alpha carbon, are there alpha hydrogens? Yes. Then finally, in the case of the alkanone, the story is quite different because the functional group is somewhere inside the molecule. So for the alkanone, this is the functional group. That carbon is alpha, and this carbon is also alpha. If we had more carbons, we would have called them beta, beta on both sides. So this is how to get alpha carbon on alkanals and alkanones. Then consider this one. Consider this compound, HCHO. This is an alkanal, metanal. Now this metanal, if you remove the functional group like we've done here, you see that it doesn't even have an alpha carbon. Therefore, it will not have alpha hydrogens. So to have alpha hydrogens, you must first have alpha carbons, which is missing in this case. So based on that, we say that this alkanal, metanal, does not have alpha hydrogens. Now, the last 2 reactions I want to show you will be dependent on the presence or absence of alpha hydrogens in an alkanal or alkanone. The first reaction is called the Cannizzaro reaction. Cannizzaro. That reaction is named after Stanislaw Cannizzaro. So what's the Cannizzaro reaction? The Calizaro reaction is said to be a disproportionation reaction. Disproportionation. What does that mean? In redox, a disproportionation reaction is one in which an element goes from a single oxidation state to 2 new oxidation states. In other words, the same element that is oxidized is the element that is reduced. There are some reactions like that where the same guy gets oxidized and reduced, unlike we have in typical cases where the oxidizing agent is different from the reducing agent. In this case, they are the same substance. So when the same substance is both the oxidizing and the reducing agents, then we say the reaction is a disproportionation reaction. Although in redox, we can have a situation like this one, where a substance goes from 2 different oxidation states to 1. That one is called syn proportionation or comproportionation. So comproportionation or syn proportionation is 2 to 1, whereas disproportionation is 1 to 2. In either case, the same substance is oxidized and reduced. So having said that, we look at the Cannizzaro reaction now. During this reaction, what happens? First, this reaction concerns alkanals. Only alkanals undergo it, alkanones don't. And the alkanals that undergo it are the alkanals that do not have alpha hydrogens. So an alkanal without alpha hydrogens is a candidate, a qualified candidate for the Cannizzaro reaction. So let's bring some alkanals that do not have alpha hydrogens. Say this one. This is benzaldehyde. Benzaldehyde. Now this benzaldehyde is one example. Another one is this one we wrote before. This is metanal. So metanal, benzaldehyde, they do not have alpha hydrogens. In this case, there's no alpha carbon at all. In that case, there's an alpha carbon which is here where I'm putting the dots now. That's the alpha carbon. But that alpha carbon has no hydrogens. So these two guys are qualified for the Cannizzaro reaction. First, because they are alkanals. And second, because they do not have alpha hydrogens. So what's going to happen during this reaction? 2 moles of each of these alkanals will be subject to treatment with base. And once they are treated with base, one of the molecules becomes oxidized, whereas the second molecule becomes reduced. And we know from first principles that reduction of alkanals will give alcohols. So my first product here from methanol will be methanol. So methanol, first product. Then when alkanals are oxidized, you remember they will give you acids. So from methanol, I expect to get methanoic acid. This is methanoic acid, but that's not my second product. My second product is actually the methanoate ion. That's how we write it. So I have the methanoate ion. So it's like saying that I'll get a salt as my other product. Yeah, depending on what metal I have here. Usually sodium, so I have the sodium there. So alcohol and alkanoate ion are the 2 products I will obtain from the Cannizzaro reaction. In this upper case, what do I get? If I treat this substance with base, I'll get the corresponding alcohol first. So I have CH2OH, that's phenyl methanol or benzyl alcohol. Then after the phenyl methanol, my second product will have the ring still, but instead of COOH, I'll have COO minus. That's the benzoate ion. So look at those 2 reactions. You see that in both cases we have alkanals without alpha hydrogens reacting with base, so that one of them becomes reduced while the other becomes oxidized. We said that is the Cannizzaro reaction. Then the last reaction we are going to talk about will appear on the board in a moment. So if you want to pause to master the Cannizzaro reaction, you could do so. Now, for the last reaction that alkanals and alkanones are to undergo now, this one is not a reaction of just one of them. You know, like the Cannizzaro reaction that we said is strictly for alkanals. This next reaction is for both alkanals and alkanones, and it is called the Aldol reaction. Aldol reaction plus Aldol condensation. So Aldol formation and Aldol condensation. Now it involves alkanals and alkanones, this time around, that have alpha hydrogens. You know, in the other case we said that do not have. In this case, alkanals and alkanones that have alpha hydrogens reacting with base. When they do so, what normally happens is the 2 molecules of alkanal or alkanone, which may be the same or different, will join together, and we say they form what is regarded as an aldol. Then if this aldol loses water, if it loses a water molecule, then it becomes, or we say it undergoes, or it has undergone in that case, the aldol condensation. So until a water molecule is lost, we can't really talk about aldol condensation. What we would have would actually be aldol formation. So look at this case. Let's say we had ethanol, CH3CHO in an exam. They give us OH like that, 2 moles. If I were to predict the outcome of this, that I am seeing base only means that I will suspect Cannizzaro and Aldol formation. But that this alkanal has an alpha carbon here with alpha hydrogens, I will know that what is to take place is the Aldol reaction. And I prefer to show you this simply. See what I mean? To get the product of this reaction, Since it is ethanol that I have, 2 moles, I'll write it this way. I'll write the first ethanol, CH3COH. Actually, I could put this H there, but I'm trying to make my first alkanal look like this. Then, my second alkanal, I will make like that. Meaning, I'm going to write the second one as CH3COH. So in either case, I have written the alkanal twice. Having written the 2 of them twice, with one looking like this and the other one looking like that with respect to the oxygen, the next things I'm going to do, please just watch, it's a very simple process. The next thing I'm going to do is, for the molecule on the right, I will locate the alpha carbon, which is this, then pick one hydrogen from it. By the time I pick one hydrogen from there, what will be left there? CH2, right? The alpha hydrogen I have picked, what will I do with it? I'll add it to this oxygen. When I add it to this oxygen, what I'll have there is OH. Then I'll join the 2 molecules together. What you are seeing there is my product. It is called 3-hydroxybutanol, and 3-hydroxybutanol is aldol itself. There are different other aldols, but 3-hydroxybutanol is like the standard. That is aldol itself. Now this aldol itself, we call it aldol partly because it has the aldehyde functional group, ald, as well as the alkanol group, all. So aldols usually have the alkanol group as well as the hydroxyl group. But there are some other aldols that actually have the ketone group now, and the alcohol group. We still regard them as aldols. Now, I have formed my aldol. So what has taken place now is aldol formation. But what if I were to make it aldol condensation? In that case, I'll have to remove a water molecule, so OH will live here, and then H will live there. So that I'm going to draw my final product after condensation, after removal of water. My final product will be CH3, then CH. Remember that OH is gone. I'll have a double bond here, then CH again. So it's against CH2, I now have CH, and then on the last carbon, I still have my CHO. This is the dehydration product of that aldol. So it is now that I'll say I have carried out aldol condensation. So starting with ethanol, for aldol formation, this is my product. But for aldol condensation, this is my product. So I have 2 different products based on formation and condensation. Now, apart from ethanol, which other compounds can we use? I'll show you 3 other reactions, 3 other aldol condensation reactions, and they will be quite special. Quite special in that each one has a lesson for you. So see this next one. Let's use propanone. So propanone is CH3COCH3 in the presence of base. They give me these 2 moles. How do I draw my product? I'll draw the first propanone to look exactly like the T there. So I have CH3 down. So this is the first one. You see it looks like that. Then the second one I will draw as CH3 again, CO, then CH3. Step 1, pick one from the alpha hydrogens, so CH2. Step 2, add it to the oxygen here, H. So this becomes a single bond. Then step 3, join the 2 molecules. This is my aldol. And if I were to dehydrate this aldol to make condensation occur now, I'll remove OH from here and remove H from there so that there will be a double bond here. In that case, I have the unsaturated ketone, which is my product for this aldol condensation. Now, what if they give me this third case, 2 moles of CH3, CO, or let's say CH3, CH2, CO, CH2, CH3. Beautiful. If I had 2 moles of this, being treated with base, how would I draw my aldol? Still by the same principles, I'll write CH3, CH2, CO, CH2, CH3. Then for the second one, very importantly, take note, I'm going to write CH2, CH3, CO, CH2, CH3. Now in this case, my alkanone doesn't exactly appear to be like that. And why is that so? And that's because this carbon here is the alpha carbon, not that one. So if I had written that one here and then put everything straight, it would be difficult for me to pick my hydrogen from the alpha carbon. As a matter of fact, I could make the mistake of picking from there, which would have been bad for me. So I have written it this way to make sure that this carbon and the alpha carbon on the other side are making contact. So that in this case, I'm going to take H from the alpha carbon, like the rule states, and then I'll put that H here, OH, and then this becomes single, and then I can join them like that. So this is the product of that aldol reaction or aldol formation. See the aldol, this compound is an aldol. Again, if you were to dehydrate this aldol, you have that OH and H living there, so there will be a double bond here. In which case you say that you've carried out aldol condensation. I'll show you one last case and that would end this video. Last aldol formation, the last one. This time it is HCHO plus CH3CHO OH minus. This is an aldol condensation that is going to take place between 2 different molecules. We don't have 2 moles of the same molecule this time, but 1 mole each of 2 different molecules. When that happens, you say that what you are carrying out is cross aldol formation, or you say cross aldol condensation, depending on how it all ends. So that in this case, I'm going to write H, C, O, and H plus CH3, CHO. So if these 2 things were to react, if we use that arrangement, we have H, we have C, O, and H. Then C, H3, sorry, I've written one, so let's write the other one first. So we have CO and H. I have written them side by side again. Then, as usual, I'll take hydrogen from the alpha carbon, so that's CH2. Then this becomes OH, and then the double bond becomes single, so I link those. This is my aldol. This compound is called 3-hydroxypropanol. 3-hydroxypropanol is an aldol. After all, it has the aldehyde group and the alcohol group. So this is cross-aldol condensation because we are using 2 different molecules and not 2 moles of the same molecule. Well, this is where we will pause. We have talked about carbonyls in some detail, and if you want further information on carbonyls, you may need to read some other books. But for now, that would be all from my end. This is the YouTube channel. You tell your friends about it, Dr. Quinty. Remember to share. Let others see. If they can't come here, send it to them. Share. And then, more importantly, subscribe. Because when you subscribe, you'll always receive notifications when I put up new videos. Thanks for watching.